Hello everyone and welcome to this complete tutorial, Simple Linear Regression from scratch. Today we are going to unlock the mathematics behind the model. We will understand three very important concepts: variance, covariance, and correlation, and then use them to build a real predictive algorithm using only pure Python. No Scikit-Learn, no NumPy, no shortcuts, just basic lists and loops. The language we are using is Python 3. And our complete focus is on core algorithms. On the right side you can see a beautiful visualization, blue data points and a purple regression line showing y equals mx plus b. This journey will help you stop treating machine learning as a black box. By the end, you will know exactly how the line learns to fit the data. So let's begin this exciting journey together. Before we jump into coding, let's understand why building linear regression from scratch is so important. The main reason is that powerful libraries hide the magic inside. We need to see the mechanics under the hood first. There are three big benefits. First, build intuition. You will see exactly how the line learns to fit every data point, step by step. No more black box. Second, better debugging. Later when your model gives strange results, you can trace the error because you know the internal math. Third, pure Python implementation. We will write the entire regressor y equals mx plus b using only lists and simple loops. No external libraries at all. The prerequisites are very beginner-friendly. Basic Python like variables, lists and loops, how to write functions, and simple high school algebra, just the equation of a straight line. If you know these, you are 100% ready. Let's move forward. Simple linear regression is one of the most important and easy machine learning models. It predicts a continuous output value called y based on only one input feature called x. It does this by finding the single best fitting straight line that passes through all the data points. The famous equation is y equals mx plus b. Let me explain each part clearly. Y is the predicted output, the dependent variable, what we want to predict. X is the input value, the independent variable. M is the slope. It tells how much y increases when x increases by 1. B is the intercept. It is the value of y when x is 0. Look at the example dataset on the left. Study hours, x, 1, 2, 3, 4. Marks, y, 40, 50, 60, 70. On the right you can see the data points and the best fit line. More study hours clearly give higher marks. This line will help us predict marks for any new study hours we choose. Now we start the real mathematics. First concept is variance. Variance simply answers, how spread out are the values of x from their average? If variance is high, the data points are far away from the center. If low, they are close together. The formula for population variance is var x equals 1 divided by n times the sum of each x underscore I minus the mean of x squared. We calculate it in 4 very easy steps. Step 1. Find the mean, average, of all x values. Step 2. Subtract the mean from every single x value. Step 3. Square each difference. Step 4. Take the average of all those squared differences. On the right you can see a nice visualization. Data points, the mean line in pink, and dotted deviations. This variance of x is very important because it will later help us calculate the slope of our regression line. Next important concept is covariance. Covariance measures the joint variability of x and y. In simple words, it tells us the direction of their relationship. Does y increase when x increases? Or does it decrease? The formula is COV x y equals the sum of x minus mean underscore x multiplied by y minus mean underscore y divided by n. Important point: covariance only shows direction, not the strength. There are 3 cases shown on the slide. Positive covariance, both move together. Example: more study hours, right pointing arrow, higher marks. Negative covariance, they move opposite. Example: more absences, right pointing arrow, lower marks. Zero covariance, no clear linear relationship. Example: height vs marks. so covariance tells us whether the relationship is positive, negative, or none. Covariance is good for direction, but it doesn't tell us how strong the relationship is. That's why we use correlation. Correlation, also called Pearson's R, normalizes covariance so the value is always between -1 and +1. The formula is R equals COV, x, y, divided by standard deviation of x multiplied by standard deviation of y. Because we divide by the standard deviations, the units disappear and R becomes very easy to understand. Look at the three examples on the right. Perfect negative, R equals 1, red dots, no correlation. R equals 0, gray dots scattered. Perfect positive, R equals +1, green dots. So now we know both direction and strength of the linear relationship between x and y. Here comes the most exciting part. We now turn our statistics into the actual regression line. First, the slope m is calculated as m equals covariance, x, y, divided by variance, x. This ratio balances how strongly x and y are related against how spread out x is. Second, the intercept b is b equals mean of y minus m multiplied by mean of x. This makes sure the line always passes exactly through the center point of the data, mean underscore x, mean underscore y. On the right you can see a beautiful graph. Rise is covariance, purple, run is variance, green, and the slope is shown clearly. One important edge case. If variance of x is 0, all x values are exactly the same, we get division by 0, and the slope becomes undefined. The line would be vertical. Time to start coding. We are now in the practical part. Step 1. Define the dataset. X equals 1, 2, 3, 4, 5 study hours. Y equals 40, 50, 60, 70, 80 marks. Step 2. Create a helper function to calculate mean. Def mean values, return sum values, len values. Then we calculate mean underscore x equals mean x, right pointing arrow 3.0 mean underscore y equals mean y, right pointing arrow 60.0. You can see the code on the right and the terminal output at the bottom. Why did we make a mean function? Because we will need the average many times for variance, covariance, slope and intercept. This keeps our code clean and reusable. Continuing the code. Step 3. Variance function. Def variance values, mean underscore val, total equals 0 for v in values, total plus equals v, mean underscore val, asterisk asterisk 2. Return total, len, values. Step 4. Covariance function. Def covariance, x, y, mx, my, total equals 0 for I in range, len, x, total plus equals, x, I, mx, asterisk, y, I, my. Return total, len, x, in our data, var underscore x equals 2.0 cov underscore xy equals 20.0. You can see the full code and terminal output on the right. Important note, we are using the population formula, divide by n, for simplicity. In real statistical libraries they often divide by n1 for sample data, but we keep it simple here. Final steps of our model. Step 5. Calculate slope and intercept. M equals COV underscore XY, var underscore X right pointing arrow 20.0 divided by 2.0 equals 10.0 B equals mean underscore Y, M asterisk mean underscore X, right pointing arrow 60.0, 10.0 asterisk 3.0, equals 30.0. Step 6. Create a prediction function. Def predict, X, return M asterisk X plus B. Now we test the model with new data. X underscore new equals 6 hours. Prediction equals 10 times 6 plus 30 equals 90 marks. Perfect. The terminal output shows slope 10.0, intercept 30.0, prediction for 6 to 90.0. Our model is working exactly as expected. Now let's understand why this exercise is so powerful. Implementing from scratch is not just coding practice, it is the key to mastering machine learning. 3 main advantages. Deep understanding. You no longer just call .fit, you know exactly how slope and intercept are calculated from variance and covariance. Better debugging. When models underperform, you can find outliers, check intermediate values, and fix problems easily. Flexibility. You can now change the algorithm, modify loss functions, or adapt it for any special case. Long-term benefits. This simple regression is the foundation for neural networks, logistic regression, and gradient descent. You gain full confidence because you can reproduce library results by hand. In interviews, companies love asking, "Build linear regression from scratch," and now you can do it perfectly. Congratulations! You have successfully built a complete machine learning model from the ground up using only pure Python. What you learned: how variance and covariance together create the slope. How correlation measures the strength of the relationship. You turned pure mathematical formulas into working code. Now it's your turn. Try it yourself. Open the code, change the X and Y lists with your own real data, for example, house size vs price, and see the new predictions. Development roadmap for you. Immediate next: add R² score and plot residuals to check errors. Refinement: change to sample variance, divide by n1, for more accurate statistics. Stretch goal: implement gradient descent to find the line automatically, or build multiple linear regression with more than one input. Thank you so much for watching this tutorial. Keep practicing, keep building, and you will become really strong in machine learning. You've got this. See you in the next lesson.